Let me first introduce Professor Yan Peng. Professor Yan Peng is obtained his bachelor from University of Science and Technology of China, USTC, and got his PhD degree in condensed matter physics in the Hong Kong University of Science and Technology in 2011. After postdoctoral training in TU Delft in the Netherlands and the Mainz University in Germany from 2011 to 2015. And he's now leading a theoretical spintronics group in the University of Electronic Science and Technology of China. His recent research focused on quantum magnons, topological magnetization dynamics, and strong coupling between photons and spins. Yan Peng, please, stage is yours now.
Okay, thank you. Can everyone hear me? I think.
Hear you clearly, yes.
Okay, thank you. Thank you for the introduction, Weber. Also thank you for the kind invitation. So it's my great pleasure to be here to introduce our recent work about the dynamics of nanomagnetism. So the title of my talk is about the spinwave frequency code. Here is my main collaborators. Most of this work was done by my postdoc, Dr. Zheng Yuwang, and with help by Dr. Huaiyang Yuan. Dr. Huaiyang Yuan is now in Utrecht University in the Netherlands as a postdoc, and Dr. Zhixiong Li is now also a postdoc in my group, and Professor Rambert Stein is from the Utrecht University in the Netherlands, and the Dr. Yunshan Chao also in the same institute of mine. Okay, here's the outline. So I'm not sure if everybody have some background about the magnetic dynamics. So I will give a very brief introduction first to spinwave, skyrmions, and Franck's code. And then I will move to the main result of this presentation. That is about the nonlinear spinwave skyrmion interaction induced magnonic frequency code. So I will first describe or modeling the nonlinear magnon-skyrmion scattering, and I will prove the existence condition for observing the magnonic frequency code, and then is the simulation result to support our theoretical predictions. Finally, I will discuss the something and then conclude my talk. Spinwave is the elementary excitations in ordered magnets. So this concept was originally proposed by Felix Bloch to explain the time dependence of the saturated magnetization in ferromagnet. So after many years, several decades development, the study of spinwave now become interdiscipline of between spintronics and condensed matter physics, because the magnon have some great advantages. For example, the propagation of spinwave in principle can avoid the electron motion, so there is no Joule heating, and the spinwave excitation can occur in both magnetic matters and insulators, and also because it can propagate over a very long distance from microns to millimeters, and you also have very wide frequency range from gigahertz to terahertz, so it can work for microwave engineering, also for ultra-fast terahertz spin dynamics. Compared to the light wave, the spin wave have very short wavelengths, so it can scale down to even to nanometers, so it can be convenient to integrate it for small devices. Also because the spin wave, sometimes it can behave as a particle, so that is the magnon. Sometimes it can behave like a wave, so there will also some proposal about the wave-based computing, which harness the amplitude, the phase, the polarization of spin waves. So overall, the magnonics now is an emerging new field. So it has it is attracting many people's attention. So this is the introduction about the spin wave. And the second, I will introduce the concept of skyrmion. This concept was originally proposed by the Britain mathematical physicist Tony Skyrmion in particle physicists. And after that, this concept or this idea was generalized to many different fields of physics. For example, in liquid crystal. So I will use a pointer. So this is the skyrmion structure in liquid crystal, and the concept also applicable in superfluid systems. And recently, the skyrmion attract many attention because it was observed in magnetism, because the magnetic community like the soliton structure. So previously, maybe you already know, people pay a lot of attention to the magnetic dome wall, which is another kind of soliton structure, because as long as we have a soliton structure in magnetic structures or magnetic devices, we can use it to decoding information or for information processing and computing. So this is also this also applies to skyrmions. So conventionally, the stabilizing of skyrmion is due to the antisymmetric exchange interaction, which is called the Yarchin-Maria interaction. Here is this is the blue arrow represent the Yarchin-Maria interaction. So if the Yarchin-Maria interaction factor is perpendicular to the neighboring to the lattice connecting the neighboring spins. So in this Yarchin-Maria interaction will stabilize a Lyell type skyrmion. So if the Yarchin-Maria interaction factor D factor is parallel along the connection sites between Si and Sj, so it will stabilize a vortex type skyrmion. So if the structure of the skyrmion depends on the behavior of Yarchin-Maria interaction. So if recently it was observed that if the Yarchin-Maria interaction is anisotropic, then it will stabilize anti-skyrmion. So as shown in figure D. So I will not go to further detail of the skyrmions, but I will say that because the skyrmion community is largely driven by the application prospect, because the skyrmion can be used to encoding the information. For example, people have proposed some structure that the presence or the absence of skyrmion can be used to encoding 1 and 0. So this represents 2 bytes. And the skyrmion can also be used to design some device with logic functions. For example, this here we have if we have 2 skyrmions, they will emerge as a 1. So if there is 1 skyrmion and the input A have skyrmion and input B have no skyrmion, then the output is skyrmion. So it is will realize all logic. Okay, because of this, for the computing and the logic applications, the skyrmion community is also developed very well. So this is so we have introduced the basic concept of spin waves and skyrmions, and then I will also introduce to you about the frequency curve. So I think every one of us are familiar with a curve because it's very useful for our everyday life. And I must emphasize that there are 2 properties, main property about the curve. The first one is that it is discrete, and the second one is that it is equally spaced. So if it is in the length space, so the curve is used to measure the length. So So how about if we change to the frequency space? So if now we have a frequency code, and the frequency code is a great invention, and this also led to the Nobel Prize in Physics in 2005. So, and the usefulness of spacing code can also be reflected in, for example, in spectrometer. For example, if we pass a frequency code through a sample, so it can be a gas, it can be a liquid, etc. Then, if we measure the output of the output signal and compare to the input, we'll find some spectral line is missing. So this will reflect that this missed spectral line must be the internal modes of the sample. So this can be used to as a spectrometer. Besides the spectrometer, the frequency also have a broad applications, including optical atomic clocks. Also, it can be also used to for the dark matter searching, and also for the planet hunting, and to probe the air pollution. And we can also use some disease diagnosis, etc. So this is the application of the frequency code. So it's so successful. So this it will also stimulate people in other community to think about if we can design or if we can propose or realize other types of frequency code. Actually, this was already done for the photonic systems. So people have already in 2014. So people theoretically proposed to realize the photonic frequency code in elastic systems through the 3-wave mixing process. And three years later, the idea was experimentally realized. So now we have photonic and phononic frequency code. They share many similarities because both of them are bosonic particles. And now we can the strategy that we should think about if we can realize the magnonic frequency code. That is the magnon frequency code in magnetic systems. But this, as we can see that this meets some difficulty. The main difficulty is that the nonlinearity in uniform ferromagnetic states usually is very weak. So this is the conventional Hamiltonian, which can be used to model spin systems. As we can see that the Hamiltonian usually contains 3 terms. So the first term is the exchange interaction, and the second term is the anisotropy. So we consider simply the case, so it is the uniaxial anisotropy. And the third term is the interfacial Yarlin-Maria interaction. In principle, it can be replaced by the Bach type Yarlin-Maria interaction. Then we have the skyrmion of vortex type. But for the interfacial Yarlin-Maria interaction, then the skyrmion is favors anile type. So if we do a small observation around the ground state, so the ground state here is not necessary to be the uniform ferromagnetic state, because we have a uniaxial anisotropy and Yarlin-Maria interaction. So the ground states can be skyrmion, vortex, etc. So in principle, if we do the Hostin-Markov transformation, so we will obtain it's similar to a Taylor expansion in mathematics. So we can have the ground state energy H0 and the linear spinwave term H2. And we also have 3 magnon interaction and 4 magnon interaction. So this is the formal expansion of the original Hamiltonian in terms of the magnon creation and the annihilation operators. So from this expression, so it will give the impression that, okay, for any Hamiltonian, we can always have 3 magnon interaction. So in this term, 3 magnon interaction term is necessary to generate a frequency code. But if we look at it carefully, we will find that if usually the 4 magnon interaction usually is much stronger than the 3 magnon interaction for uniform ferromagnetics. So later I will show you the case because for a uniform ferromagnetic state, the 4 magnon interaction comes from the strongest exchange interaction. So the exchange interaction contributes to the 4 magnon interaction. However, if we neglect the Hamiltonian interaction, and we will know that the 3 magnon interaction terms comes from the dipolar interaction. So the dipolar, however, the dipolar interaction usually is much smaller, much weaker than the exchange interaction. So for conventional magnetic device, the H4, so the 5 magnon process sometimes can be stronger than the 3 magnon process. So this gives us a dilemma that so we need 3 magnon interaction, but the 3 magnon interaction is very weak compared to the 4 magnon interaction. Okay, this is a problem. But before we move on, we will first show you a no-go theorem that states that for 2-dimensional or higher dimensional case, the 4 magnon process can only contribute to cannot contribute to the frequency code. So this can be simply reflected in this diagram. So if we consider 2 inputs, K1 and K2, so if we assume energy conservation and the momentum conservation, these 2 laws, then we'll find that the output, the new mode K3 and K4 will share the same circle as the K1 and K2. So if we calculate the input, calculate the output mode, we'll find that for given K1 and K2, the 4 magnon process can generate a continuous spectrum, so which is not the discrete one. So for a frequency code, we need discrete mode. But for 4 magnon interaction, so only generate a continuous output. So it cannot generate the frequency code. So if that's to say that if we want to generate the frequency code, we need the 3 magnon processes. But as we stated earlier, in uniform ferromagnet, the 3 magnon processes comes from the dipolar interaction or Hamiltonian interaction. But these 2 types of interaction usually is much larger and much weaker than the exchange interaction. For example, it's about 10%, at most 10%. For example, the Hamiltonian interaction is about 10% of the exchange interaction. So this interaction is too weak to generate the 3 magnon processes to be compatible to the 4 magnon processes. However, recently we find that if the ferromagnetic state is not uniform, that means that if we have some spin textures, for example, the skyrmions, doping walls, or vertex, we have found that this because of the large magnetic gradients, and the 3 magnon interaction is significantly enhanced. So this is the example, is a simple example I will show you. So what's the 3 magnon processes? So let's first look at fig 1, fig 8. So if we have 2 input modes, Ki and Kb, then the 3 magnon process will generate a single K. So this process is called confluence. So we have 1 plus 1 is equal to 1. So this is the confluence. So we should also not be surprised that we have 2 magnons, but we only generate 1 magnon. So this means that the magnon number is not conserved. So this is very natural for in bosonic systems. So for the some other quasi-particles like photon and phonon, so their particle number is also not conserved. So in very contrast to the fermionic case, for example, the electron. So for the boson, so the really important conservation law is energy conservation and the momentum conservation here. So figure 1 reflects the confluence process. Figure B and C represent the 3 magnon splitting, which means that we have 1 input magnon Ki, and it will split into 2 modes, K1 and K2. So this both confluence and splitting are called 3 magnon processes. So in 2008, we have a design theory to originally the theory is to detect the proposal is to detect the localized mode propagating along domain wall. So in that case, so if we have Ki as the instant spin wave, and then we have a Kb propagate along the domain wall, and the frequency of Kb is much larger and is much lower than the FMR, than the ferromagnetic resistance resonance frequency. So this mode is spatially localized around within the magnetic domain wall. So if these 2 modes K and Kb interact with each other, for example, for the confluence process, we observed a new mode. So for example, we have we let the Ki is 32 gigahertz and the Kb, the frequency is 6 gigahertz. So if we input these 2 modes and we measure or we detect the output mode here, so we'll find 38 and 26 gigahertz. So the high frequency modes correspond to the confluence process, and the low frequency modes correspond to the splitting. So the basic conservation law is summarized in this table. So we only have required energy conservation and momentum conservation. So and this momentum conservation is restrained momentum conservation because there is only exist spatial invariance along the domain wall. So the momentum conservation should be projected along the z direction. So it's not a global kind momentum conservation, but it's a projected one because only in along the domain wall the spatial invariance is reserved. Okay, I'm happy that since our work after our work and 2 years later, and this proposal, also this phenomena was observed experimentally. So, but not in magnetic domain wall, but instead they observed the stimulated the 3 magnon splitting inside the magnetic vortex. However, this is still not the frequency code as I want to share you today. It only reflects that for inhomogeneous magnetic textures, there exists 3 magnon processes, even we consider the dipolar interaction. So as we introduced to you, for a uniform ferromagnet, the dipolar interaction is indispensable for 3 magnon processes. But for non-uniform ferromagnets, ground state, the dipolar interaction is not necessary. So what we need is the large magnetization gradient. So this magnetization gradient can contribute to a significant 3 magnon process. Okay, so we already introduced to you about the spin wave and the skyrmion and the frequency code. Now we will move on to their mutual interaction. For example, I will show these 2 figures show you the spin wave skyrmion scattering. So in this field, the scattering itself already can give you us a lot of fantastic physics. For example, the scattering of spinwave by skyrmion can generate some skyrmion, so the spinwave Hall effect. And also if the spinwave can also drive the skyrmion propagation. So due to the momentum transfer or angular momentum transfer. But all these interaction works in the linear regime. So if we want to see the frequency structure, the macron frequency structure, we need to go to the nonlinear regime. And specifically, we need to have 3 macron interaction. So this is the figure schematically show the nonlinear macron skyrmion scattering. So let's look at this figure. So if we consider a 2-dimensional ferromagnet, as shown here, it can be a very thin magnetic film. And this thin film can be a copper platinum heterostructure. So the copper is a standard ferromagnetic material. And if we deposit the platinum on top of it, it can generate very strong or sizable interfacial Yarshins-Maria interaction. And this interfacial Yarshins-Maria interaction will stabilize a layer type skyrmion. So as shown here, this is very localized magnetic defects here. Conventionally, the skyrmion is regarded as a rigid body. It means that it has low internal excitations. However, if the external frustration is strong enough, it can will generate or excite its internal excitations. So here we are focused on one of the internal excitations. So this is it is referred to as the bracing mode of the skyrmion. So later I will show you what's the meaning of the bracing mode of the skyrmion. So in this 2-dimensional ferromagnet, if we excite spinwave here in this bottom, for example, it can be done through spin transport torque or microwave antenna, etc. So there are many approaches to excite spin waves. So if we excite a spin wave here and then let the spin wave to propagate to hit the skyrmion. So if the amplitude of spin wave is strong enough, it will excite the skyrmion's internal mode. This is labeled by omega r. This is the bracing mode. So if the criterion for the 3 macron interaction is satisfied, it will generate branches of new modes. So shown on this top figure. So this in the middle is the instant spinwave mode omega 0. So there are also many sub-bands, sub-branches, Flex mode, and with equal distance omega r. And this omega r is exactly the bracing frequency of skyrmion. So under the new mode, mathematically can be described by omega naught plus n times omega r. This n is arbitrary integer. So if we have many spectral lines, this spectrum can be regarded as a macron spinwave code. So this is our idea, and mathematically it can be modeled by a formal by a Hamiltonian like this. So we can start from the Hamiltonian as I showed you previously. So in this Hamiltonian can include the exchange interaction, uniaxial anisotropy, and the interfacial Yarshins-Maria interaction. So if we do the Hostin-Primakov expansion, we can go to the spinwave Hamiltonian. The first 4 terms are the linear Hamiltonian. The first one is the propagating, the instant spin wave. And the second one is the bracing mode of the skyrmion. And the third and the fourth represent the confluence and the splitting of between omega 0 and omega r. And the GP and GQ represent the nonlinear interaction between skyrmion and the spinwave. And the last term is the driving. And omega 0 is the driving frequency. Okay, so if we transform the Hamiltonian into a rotating frame, so we can annihilate the time dependence of the Hamiltonian, and the Hamiltonian now becomes time independent, and then we can solve the Hamiltonian. Because the Hamiltonian is nonlinear, it cannot be solved exactly, but it can be done perturbatively. So first of all, we will use the mean field approximation, and that means that we neglect the nonlinear interaction first. Then we will obtain the spinwave dynamic. We will solve the spinwave dynamic equation and obtain a trivial solution. It means that the spinwave is excited only by the external driving, and the spinwave frequency is exactly matching the excitation frequency. And the nonlinear generations, the magnon mode, the nonlinear population of the Bliss mode and the confluence and splitting is 0. So this is the linear response. So if we can then analyze the stability of this linear response solution, and we can obtain the critical field or the threshold field. So beyond which the nonlinear process can occur. Otherwise, it will be suppressed. So we indeed find the critical threshold as labeled by HC. This is the critical value. It means that if we want to see the 3 magnon process or the frequency curve structure, we must require the amplitude of the microwave field is larger than this figure. So in order to verify our theoretical proposal, we run some simulation with use Mumax package. So we consider the material of copper and platinum crystal structure and discrete the 2-dimensional film into this cell size, and shown in figure A. We can see that we consider film of size 1 micron across 1 micron, and there is a small Nile type skyrmion in the middle. So in order to get the useful information about the magnon spectrum, we first analyze the excitation of the whole film. So we first consider if this film has no skyrmion structure, that means that it is a uniform ferromagnetic state. Then we can only observe this 37.7 gigahertz. We can only observe this spectrum. However, if we have a skyrmion in the middle, in the center, then the spectrum changed a little bit. So besides the strongest peak at 37.7 gigahertz, there is another one, 30.7 gigahertz. So if this is obtained if we analyze the magnetic variation along the x direction. So similarly, we can analyze the spectrum of delta mg. Delta mg means the variation perpendicular to the plane. We can see that besides these 2 strong peaks, we identify a rather very weak but still sizable peak at 8 gigahertz. So this is the whole information we obtained by analyzing the spectrum of the thin film without skyrmion and with skyrmion. So then we need to clarify what are they. So if we can use a sinusoidal excitation with the same frequency, for example, we first use a sinusoidal excitation at 8 gigahertz, we will find that the skyrmion size here, the skyrmion size, the skyrmion radius RS periodically oscillates. It means that it kind of looks like a prism, right? So the Skirmion size, the Skirmion radius is sometimes expands and sometimes shrinks. So it's like a prism. At the same time, the center of the Skirmion does not change. So it keeps static. The Skirmion center is static, but its size is shrink and expand. So it's we therefore conclude that the 8 gigahertz represent the prism mode of the Skirmion. Let's look at the 30.7. So similarly, we analyze the behavior of the Skirmion, and we find that the Skirmion center, the Skirmion size does not change very much. So this line is almost a straight line. So it means that Skirmion size does not change, but the Skirmion center, so it's oscillates periodically. So this red and blue represent the x and y coordinate of the Skirmion center. So this Skirmion center is represent the gyration mode of the Skirmion. And naturally, we also analyzed the most significant the peak, the 37.7. So this peak represents the ferromagnetic resonance peak. So we have no every mode come from the Skirmion, the bracing and the gyroscopic mode. Because this mode, the bracing frequency is rather low, rather small. So we think this should be useful to generate the frequency code, and the distance between two codes should be exactly be 8 gigahertz. So let's see. So what the numerical simulation are. So this is the simulation result, and this is the setup. So we consider same film, 1 micron plus cross 1 micron, and we have a Skirmion in the center. So in the left side, we use a microwave antenna. So this is the microwave field inject through this antenna. It will generate spin wave of frequency omega 0. And the H0 is the amplitude of the field. So firstly, we consider very weak microwave field. So the field amplitude is 10 milli-Tesla. And we find that we can observe the 3 peaks. And the strongest one, of course, is the instant spin wave. So this is omega 0. So we have set it to be 80 gigahertz. And we also observe omega c, and the omega c is the ferromagnetic resonance, the FMR frequency. And we also observe the frequency doubling of the instant spin wave 2 times omega 0. So nothing have new mode also observed. So no new modes also was observed. Then we increase the field amplitude to 100 milli-Tesla. So I observed that a new mode emerging in the low frequency side. So this omega r is appearing. So this omega r at 8 gigahertz exactly it is the prism mode of the Skirmion. And besides this omega r, we can not very clearly, but we can still see some new mode at both sides, around both sides of the instant spin wave, 80 gigahertz. However, if we increase the field amplitude to 200 milli-Tesla, we will find a very clear signal of frequency code. And all this code and the distance between any neighboring peaks is exactly 8 gigahertz. So this is the prism frequency of the Skirmion. So we can clearly observe a frequency code structure in this system, in our systems. So this is the three cases represent the weak and the intermediate and large field amplitude to give you a sense that how we can generate the magnon frequency code. So this is the detailed analysis, detailed simulation results. So if we continuously increase the field amplitude, we will find that there indeed exists a critical field around 120, I guess, here. So only when the field amplitude is larger than 120 millitesla, we can observe the frequency curve structure, and the distance between the two peaks is exactly the blazing frequency of the Skyrmion. So we therefore propose that based on our previous theory, we can compute the critical frequency, and it compares reasonably well with the simulation result. So the dots, the symbols is the simulation results, and the solid lines, the solid curves comes from the theory. So this is the second, this is the first result, and the second finding is that there exists a frequency window. So only when the instant spin wave frequency lies inside this window, we can observe the frequency curve. So in our case, the frequency window lies between 70 to 80 gigahertz, as shown here. So our theory can also capture this behavior very well. So the symbols also is the symbols comes from the micromagnetic simulations, and the solid curves is the theoretical result. So the theory can describe the window behavior for the frequency curve reasonably well. So if we increase the input frequency, we can see that in the high frequency region, we can also observe frequency curve structure, although it's not that strong as in the low frequency region. It can be, still can be seen here. So it represents that if we list the spinwave system can be a very good platform to study spin waves, because its frequency range is tunable. So we can even design a dual spin wave curve structure in the thin film device. So as I introduced to you earlier, the spin wave can drive the Skyrmion propagation. So this actually it is indeed observed. So if we as shown in figure A here, so if we trace the center of the Skyrmion, we can find that the Skyrmion center moves toward the frequency source, but this with a very slow velocity, which is less than 1 meter per second. So although the frequency the spin wave can drive the Skyrmion propagation, the Skyrmion propagation contributes the contribution of the Skyrmion propagation is negligible to the frequency curve structure. And if we analyze the output frequency, we can see that the frequency, the spin wave is highly anisotropic because of the chiral structure of the Skyrmion. So here is the discussion. So we have used the magnetic Skyrmion as an example to show you the generation of Skyrmions. And this it can be the Skyrmion. The frequency curve can also be generated in other magnetic solitons, for example, the anti-Skyrmion vortex and bimirror. So I will show you very briefly the magnetic vortex can also be used to generate Skyrmions. We know that in magnetic vortex there exists many different modes: the gyrotropic mode and the azimuth mode, and the longitudinal mode. And we can see that the nonlinear interaction between the gyrotropic mode and the azimuth mode can generate the magnetic frequency curve. And they're different from the magnetic Skyrmion, which can exist in very large films. the magnetic vortex usually can usually exist in confined geometries, but there is another advantage that in these confined geometries, the spin waves can carry orbital angular momentum, so which is absent for the spin wave in conventional thin films. So we have found some selection rule for the spin wave cope in generate in vortex structures. So, but I will not go to very detail about this. But I only want to emphasize that the basic physics is very similar. So, but because of the rotational symmetry and the confined geometries, there exists the extra constraint, which is the conservation of orbital angular momentum. This conservation of orbital angular momentum is actually absent for the spin wave Skyrmion interaction, and because there is no rotational symmetry, so there is no conservation of orbital angular momentum. Okay, the other advantage to use magnetic soliton to generate a spin wave cope is that the breathing frequency of Skyrmion is inversely proportional to the square of a Skyrmion radius. So if we can tune the spin wave radius, the Skyrmion radius, so we can tune the spacing of the frequency cope. So there are very many methods to achieve this purpose. For example, we can use magnetic field and the electric field and the string to tune the Skyrmion radius. So we can, through these approaches, one can tune the spacing of the frequency cope. But there is an ambitious purpose for the frequency, for the magnon frequency cope, because we already see the success of optical frequency cope. But how about if we want our magnon frequency cope to compete with optical frequency cope, so we need very high Q factor of magnons. But this is a great challenge for the magnonic community, because the best magnetic material is lithium iron gallium, and it's because it has the smallest gearbolt damping. But then also there is very high quality factor, but its quality factor is still much lower than its acoustic and superconductor or optical counterparts. So we need to significantly increase the quality factor of magnons. So there we have one proposal for this purpose. So if we should find a way to reduce the gearbolt damping, or even realize the negative gearbolt damping, and we find the approach which is based on the optomagnonic approach to its purpose. So we consider a spin here, and we inject 3 lasers to interact with it, because the optical frequency is much higher than the spin frequency. So the interaction process is actually parametric and non-resonant, as shown here. So we have found that in the far below detuning regime, so the night matter interaction, the night spin interaction can generate an effective gearbolt damping, and the sign of the gearbolt damping is tunable by the detuning parameter. It can even be the effective gearbolt damping can be 0 or even negative. So this could be approached to increase the quality factor of magnon dynamics. So if this is realized in experiment, so our magnon frequency cope can be possibly compete with the optical frequency cope. So this is the conclusion of my talk. So I have predict magnonic frequency cope generated by the 3 magnon interactions, and our results can be extended to antiferromagnetic system. So in this system, we have a terahertz frequency code. And our work opens the door for magnetic texture-based nonlinear magnonics. And our finding would be useful for short wavelength spin wave physics citation and spin calibrations. And more details can be found in this paper. And this figure was taken by Dr. Zhengyu Wang last year, the year before last year. When he do the simulation and look at outside the window, they find some cove structure in the sky, and which means reflects that the cove structure is ubiquitous in nature, and our spin wave frequency is just one example. Thank you very much. And this is my group.
Thank you, Peng. Any questions from the audience? Feel free to ask. So maybe I first start. So you, for the detection of this one, you mean we can use the Brillouin scattering, right? For this, and it's determined by its frequency, right? So, so currently, what determines this 8 gigahertz this frequency spacing? So you mean for antiferromagnetic material, you can get the terahertz, right? Then you can use Raman maybe to propagate already.
Yes.
Raman scattering.
Yes.
So what determines this 8 gigahertz?
8 gigahertz is actually the internal mode. It what is it determines, actually it can be determined by the skirmion size.
Skirmion size.
Yes. So it is the skirmion size is small, and is the bracing frequency can be very high. So if the skirmion size is large, and the bracing frequency can be lower.
So here you also simulate the 72 and 88 gigahertz, right? This is
no, this is the output. So the input is, so we only use one input, singular is 80 gigahertz. So maybe I did not see clearly. So this is the simulation setup. So we only use the input microwave antenna. The input frequency is 80 gigahertz. So all other modes is produced by the nonlinear processes.
So this nonlinear process determines on skirmion size.
Yes, yes.
Okay. So then for the antiferromagnetic, you mean you can push it to terahertz?
Yes. Yeah. Actually, we have run some preliminary simulation, and we can find that for conventional antiferromagnetic materials, we can observe the frequency curve as well. But the spacing of the curve is about 100 gigahertz. So the spacing between two peaks.
Yeah, then it goes to the Raman scattering regime.
Right. So in this, for the spin wave in ferromagnet, it can be the detection of the spin wave curve can be done by the microwave technology. I think it's already enough for that.
But this one you can still use a Brillouin scattering to do it.
Yes, in principle, yes. I think that the microwave, the micro-focused BIS is a powerful approach to detect the spin spectrum.
Any more questions from the audience? Any more questions? So for this one, can you detect in the time domain as well? I believe so, right?
Which one?
For this frequency comb, you can also detect in the time domain, right? Because the time domain seems is a slow process. Right?
Yes. Actually, we obtain numerically we obtained from the time domain, right? We record the magnetization dynamics over a long time and do the Fourier transformation. We get the spectrum.
But experimentally?
Yeah, but experimentally, I think, as you said, the BIS it can be done in the frequency domain.
Mm. Okay. Any questions? Still have some time. So okay, so if no questions, let's stop here. And if you have any question, feel free to write email to Professor Peng as well. And thank you for your attention. And thanks Peng again.
Okay, thank you, Bro. Thank you, everyone.